Hello everyone. In your physics studies, you may have come across the idea that as you move further away from a charge that has an electric field, its electric field gets weaker. The field lines spread out. So imagine my surprise when I came across this situation where the electric field does not get weaker, even in theory, no matter how far you are away from the thing that's causing the field. So this situation is that of the infinite charged sheet. Even though it's theoretically infinite, it really did surprise me that the electric field never actually decreases in strength, no matter how far you go away from the charged sheet that's causing this field. And in this video, I'm going to walk you through the mathematics and explain why this is the case. I'm also going to explain a little bit what happens in real life when a sheet is not infinite, and why it does make more sense once you think about it in the real world. So, to begin, suppose you've been assigned the task of figuring out what the electrical force, a charge outside of an infinitely large, positively charged sheet of electrically charged material, say, experiences. What force does it experience? Well, let's simplify this a bit and look at only a unit positive test charge. So the charge is not putting any force on the sheet. We don't need to worry about that. The sheet is just always there, always in its original position, and just exerting some force on the positive unit charge. So in essence, we're trying to find the field strength at a certain distance away from the field. So the first argument to make, the first logical point you can make, is that because it's an infinite sheet and it's completely uniform, the sheet in its entirety has the same amount of positive charge per unit area, sigma, coulombs per meter squared, which I'm going to refer to as the charge density per unit area, or just the charge density. It should not matter where the actual positive test unit charge is, except for how far away from the plane, how far away from the charged sheet we're looking at. So, in essence, we've removed 2 dimensions from this 3-dimensional problem already. All we're looking at is how the distance away through the normal from a certain point to the field, from a certain point around the sheet to the sheet itself. Let's call this distance h for, say, height above the plane. We're trying to see how this distance affects the electric field at the point here. And as I'm going to show you, it actually does not affect that electric field at all. No matter how far you are away from it, electric field doesn't change, stays constant. So, to figure out the electric field from an entire sheet of charges, it's first wise to consider how you could divide this sheet in order to sum all of the forces from every single charge on the sheet up together. What I thought was, because this situation is what I would call radially symmetric, in the sense that if you have some sheet and there's the charge hovering above it, a certain distance above, then any charge which is a certain radius r away from the point where this normal line goes through, from the charge to the plane, any charge which is here is going to have the same effect in terms of the vertical component of the electric field it causes on this point in space. For instance, the charge here might cause an electric field that goes like this. The charge here might cause an electric field that goes like this. And the thing is, because you've got a complete circle, in one half of the circle, you've got entirely charges that sort of are directed towards this side of the sheet, and in the other side of the circle, the charges exactly correspond and cancel out, such that if you added up all the horizontal components of the electrical forces of these charges that form a circle around the sort of landing point of this point in space, it's going to look like a circle, basically, because you've got electric field vectors in every direction imaginable, so surely they must cancel out, because every horizontal vector will have an opposite vector on the opposite side of the circle. So we're only looking at the vertical component of the force because we're running with the assumption that, or it's really more of a justified statement, that the charge, no matter where it is, will experience a electric field that is normal to the plane. And more simply, you can just say that that's a logical consequence of the fact that the plane is completely uniform. It's completely symmetric no matter which direction you're looking at from the perspective of this point. So what we're going to do is split the plane into infinitesimally thin sort of rings of charge with a width, a very small width, a very small part of the radius, delta r, or dr if you prefer, for it to be literally infinitely small such that it's 0. And within this sort of area, we want to use the area of this, which is going to be 2 pi r, which is the size of this circumference, multiplied by the thickness of this band, which is dr. And that's the area of a certain ring of charge a certain radius away from the center. So if you multiply that by the charge density per unit area, you find the amount of charge that is on this ring. You may be able to see where I'm going with this, because if you are familiar with this notation, small delta or small d times some variable, you might think I'm going to go ahead and integrate it, and that would be correct, because what I'm trying to show here is that you can find the total force, the total electric field at a certain point by summing up the electric field from all the charges on the entire plane. And organizing these charges into circular bands happens to be an extremely convenient way of doing so, because you get this integral in terms of the radius. You're eventually going to integrate something from a radius of 0, nothing here, to a radius of infinity, which is the whole rest of the plane. R is 0 to r is infinity. We're going to be integrating something with respect to dr. And this integral, ideally, should be equivalent to the integral over wherever it's applicable of the entire electric field, just the vertical components of them. Like, if dEV is the infinitesimally small vertical component of the electric field that is caused by the charges in a certain circle, each dr is going to correspond to 1 dEV, simply because this dr has a literal meaning of the charges contained a certain radius away from the center, and these charges are going to exert some, like they're going to contribute some small electric field to the overall electric field here. So basically, by summing up all of the infinitely small electric field contributions from these charges here, 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 and so on until you go to infinity, you will have gotten the total vertical component of the electric field, i.e. the total electric field that is acting on a certain point, a certain height above the plane. So we've started with the radius, and already we've progressed to an expression about the charge a certain radius away from the center. Now, if you consider this charge to be accumulated into a point that just happens to be the same radius away, which I would say is a fair model simply because, as I said, this situation is radially symmetric. No matter what way you look from the center of the plane, the infinitely charged sheet, the infinite charged sheet will look the same. So all the horizontal components of the electric field cancel out because there's always a corresponding bit of charge on the opposite side of the circle to do that for you. We're going to say that the entire charge that is within that infinitesimally thin ring is concentrated at a point, and this is a charge dq. We're going to say that the point we're interested in has a height h above the plane, as I mentioned earlier, and we can use this information to figure out the distance from this charge to this point, and from that, as well as with Coulomb's law, which is basically the statement that an electric field is Coulomb's constant times the charge causing the field divided by the radius between the charge causing the field and the point in the field squared. We can find an expression for dE, which is the sort of electric field in this direction, although we have not yet accounted for the fact that we're only looking at the vertical component. So this Coulomb's constant, it's a fundamental constant of nature. It's something that is known and we don't need to do any extra work deriving it. This charge Q is going to be dQ because we're looking at just an infinitesimally small charge from an infinitesimally small area. And this radius between the 2 points in question is going to be this hypotenuse of the triangle. So because we just want the radius squared, we can use Pythagoras' theorem to know that that radius squared is h squared plus r squared, and as a result we can say that the electric field we're dealing with from that charge is k delta q over h squared plus r squared. So of course if you didn't manage to follow along this far, then naturally just go back and rewatch the parts you need to. And if you have any questions, of course you are free to leave a comment. If these videos have been interesting so far, then be sure to subscribe and share them with your friends, because it would really help me and I'm extremely appreciative of it if you do. And that's basically my self-promotion out of the way. Let's continue with the problem. So we want to go from delta E to delta EV, which is the vertical component of this electric field, which is the only actual contribution to the overall electric field that a ring of charge can give, because, as I mentioned, the horizontal components of the electric field from each charge in the ring gets cancelled out by the charge on the opposite side of the ring. There's a police car driving by on the highway next to my home. So basically, what you have to do is just a simple kind of vector decomposition. We know that this side is going to be the root of h squared plus r squared, so we know that the ratio between dE and the vertical component dEV is going to be the ratio of h squared plus r squared to h. So basically you can say that dEV is going to be h over the root of h squared plus r squared. And for context, that is cos theta, where theta is this angle from the normal to the point on the electrically charged sheet that you're looking at. So it's sort of what angle away from my center line of vision are we considering at the moment. And this idea of this angle theta is going to come in more useful later when I talk about sort of how this situation behaves when it's not an infinite sheet. Alright, so delta E here, delta EV here. Let's go all the way back into putting this in terms of delta r, such that we can integrate from r equals 0 to r equals infinity, because we know that the integral bounds r equals 0 to r equals infinity have sort of the legitimate physical meaning we're looking for, that is, to integrate the electric field over the entire plane. So we just want to integrate DEV wherever it's relevant, and we don't know where it's relevant, but we do know how to phrase where it's relevant in terms of r. This becomes the integral of, this should be multiplied by d, the integral of h over root h squared plus r squared dE, and dE in terms of dq becomes, well, this nicely has this sort of h squared plus r squared term to the power of 3 over 2 at the bottom, and I think that's pretty neat. Becomes k over h squared plus r squared to the power of 3 halves dq, or dq if you prefer, delta q. Putting this in terms of area, we get k sigma unit area over h squared plus r squared 3 over 2. And this becomes, if we account for the fact that delta area is 2 pi r delta radius, we get, oh sorry, there should be a factor of h up here. So hk sigma, right. hk sigma 2 pi r delta r over that whole thing with the square root in it somewhere at the bottom. So this would be integrated from 0 to infinity to ultimately give us the entire electric field E that is experienced by a point height h above the plane. So let's actually integrate this. That's where this problem has been leading up to. The cool thing about using calculus in physics is that although in school I expect at IB level, and certainly at IB level, perhaps not at A level, and definitely not in more complicated qualifications I expect, such as like the German, Indian, or mainland Chinese math and physics high school qualification, although that's a discussion topic for another day. I'm fairly certain that you don't often go through this process of constructing an integral from a physical situation before mathematically solving it. But it is a fun and satisfying thing to do, and it is a very useful skill if you find yourself interested in trying to model these more complicated situations, or situations in physics that involve infinite something that you need to add up entirely, or something that you can't really add up easily. But anyways, yeah, that's basically what I wanted to comment on, is that this is a skill that can be learned, and likely if you're doing physics or engineering or something like that at university, you will learn this skill in the first year at least. I don't know, I expect that this will be covered in my first year at some point, because for those of you who know me personally, of course you know that I'm going to university next year. But anyways, more on that later, or in another video. We want to integrate this portion, this integral, from 0 to infinity with respect to r. The first thing that jumps out to me is that you could likely do a u substitution, where this thing inside the power of 3 over 2 is u, because there is a 2r dr, which is basically the differential of r squared plus h squared being a constant. So let's try that. If u is h squared plus r squared, or u of r is h squared plus r squared, then du by dr would be 2r, because you're just doing the power rule on this and cancelling this out completely, and thus du is 2r dr, and we do indeed have this term in the top of our integral. So at the same time, let's convert our bounds, because I have decided we're going to do this u substitution. U when r equals 0 is h squared plus 0 squared, which is just h squared, and u when r equals infinity or the limit of r as r goes to infinity is going to be h squared plus infinity squared, positive infinity squared, which is just positive infinity, basically. So in the end, we have this integral from h squared to infinity of, well, 2r dr get cancelled out and replaced with a du. And we're just left with hk sigma pi, or the height above the Coulomb constant, the charge density, and pi. So hk sigma pi du over u to the 3 over 2. And so simply with a power rule, you can integrate this to find minus 2 hk sigma pi over u to the 1 over 2. You can check this yourself. It's u to the minus 1 over 2 integrated becomes minus 1 over 2 times minus 2 is 1 u to the minus 3 over 2. That's just the power rule expression of this. And the bounds are infinity and h squared. And remember, because it's an indefinite integral, just simply because this u has no real physical meaning, I suppose you could say it has the physical meaning of sort of the distance away that a particular point is, depending on the radius. So you're integrating like the squared distance. So you're integrating from this distance is root u to this distance at the quote-unquote end of the sheet is root infinity. But anyway, that's for another time. Or I mean, like, you can think about it yourself, the physical significance of this dummy variable u, simply because it's h squared plus r squared, which is the square of the distance of a particular charge from the point in question. But it's not too majorly important to the solution of this actual integral. We've got a minus sign in here, so we're going to flip the bounds for convenience. 2hk sigma pi over the square root of u from h squared to infinity. And so evaluating the bound to h squared, you get 2hk sigma pi over the square root of h squared, which is just h, minus 2hk sigma pi over the square root of infinity. And the square root of infinity will go to infinity, positive infinity, that is, and therefore this entire term will go to, where did my stuff go? This entire term will go to 0. So overall, you're just left with this 2hk sigma pi over h, and here's the amazing thing, the height cancels out. So no matter how far away you are from the infinitely charged plane, that height term is going to cancel out. And you'll find that basically you're left with 2k sigma pi, which doesn't vary with anything except for Coulomb's constant, which is a fundamental constant of the universe, which doesn't vary, of course, and sigma, which is the charge density per unit area on this sheet. So the only thing that affects the electric field from an infinite sheet, no matter how far away you are, is the charge density and not your actual position relative to the sheet. If there was a universe that simply had one enormous sort of plain charged sheet in it, there would be the same electric field on one side of the sheet everywhere in the universe, and there'd be the same electric field on the other side of the sheet everywhere in the universe. Isn't that crazy? Like, the first time I found this, I was so, like, shocked, because my intuition would always tell me that as you move further away from something charged, the electric field strength should decrease, but this is not the case, and hopefully now you guys can believe me, because I've just shown you how to show that this is the case. So I don't know, I thought that was just really exciting, and it was something I wanted to make a video about. So yeah, that's basically the crux of this video, the fact that the infinite sheet has the same electric field no matter how far away you are. So let's put a cap on that for the moment. Let's put a cap on the infinite sheet for the time being. And let's try and think about the finite case. Okay, so we're gonna sort of branch off from this step of the integral over here and look at a finite case. One thing I found when investigating with this integral was that basically you have a hk sigma 2 pi. If you have a certain radius where the sheet finishes, so say you've got sort of like a circularly charged plate, a circular charged plate of radius r, and this is over h squared plus r squared to 3 over 2. What you are doing is sort of, you've got this charged plate here, you've got your electric field sort of point of concern here, and you're integrating from r equals 0 to r equals r. So if you want to think about it in terms of the angle, you're integrating from theta equals 0 to sort of this angle here, how much of your vision is occupied by the plate. So basically, if you do the same u substitution, you'll find that you'll be integrating from h squared to h squared plus r squared. That whole thing du. And once you plug it into the final integral you get, with the bounds of h squared and h squared plus r squared, sort of this 2 pi sigma k h over root of u, you'll find that if I just move this out here for a second, 2 pi sigma k h 1 over root u h squared to h squared plus r squared, you'll find this becomes h over h minus h over root h squared plus r squared. And you may realize that this expression, h over root h squared plus r squared, is quite familiar, and that's because it is the cosine of this angle here. It's the ratio between the height here and the root of h squared plus r squared, which is sort of the distance to the edge of the plate that you're looking at. So this is cos theta, where theta is defined from the physical situation as being sort of how much of your vision does the plate occupy, how much of your vision does the electrically charged plate, and I suppose it approximates to work for most shapes, or most sort of round shapes. I guess a square would also work, but anyways, I'm not going to get into that. Let's consider it a circle for now. This is cos theta, this is 1. You get that the electric field from a finite plate is only dependent on the angle of your vision that the plate occupies if you are located at a particular point. So you can kind of see how, because like when you're right up next to a plate, it occupies this much of your vision. The angle is very large. The angle is going to be, this angle is going to be close to 90, and as it approaches 90, cos theta 90 degrees. As it approaches 90 degrees, cos theta will approach 0, and this will approach 2 pi sigma k, being the same as the infinite plate once you're right up next to it. But say you move further away. Say you are so far away that the plate looks like this tiny thing here, and you're right here. So if the plate is occupying such a tiny amount of your vision, then cos theta is going to go towards 1, and the electric field you experience, 2 pi sigma k, one minus cos theta. This whole expression is sort of not as meaningful anymore. Wait, I've lost my... this expression is not as meaningful anymore, and it's sort of more worthwhile to calculate this with k sigma a over, because this is q, k sigma a over r squared, basically. I don't know, I just thought it was a really interesting thing to think about, was the fact that it scales with the cosine of this angle, and that seems like such a beautifully simple solution to this problem. I thought it would be harder than that because you're summing up something that goes on infinitely, but anyways, this is sort of the intuition you can get. And so what I realized is, if the force is going to be similar as long as the angles are similar, if you think about a capacitor, like this is the reason why you have the same charge building up in the internal segment of two series capacitors with a power supply on the outside. Because of course, this internal segment of the capacitor does not have any electromotive force directly supplied through a conductor. But what it does have is the electric force from the electric field of this thing and this thing. So say you're some electron somewhere in this whole electrically conducting body. As long as the plates are close together and occupy a similar angle of your vision, the only thing that will allow the E you experience to be close to zero is if the charge on this plate is approximately equal to the charge on this plate. And because, or so sort of the charge density being equal and opposite. Although in practice, because the areas are often the same, it just means the charge is going to be the same. So overall, that's why you get, even within this internal part, some minus q plus q plus q minus q at equilibrium when the electric field is zero on a particular thing. The plates on one side are going to have equal and opposite charges, and the plates on the other side are going to have equal and opposite charges. And that's why capacitors work like this. That's why there's going to be a positive charge here that is equal and opposite to the charge here, and vice versa for these two, which further explains a bunch of properties of capacitors that you can investigate on your own time. So we've come to the end of this video. Thank you so much for watching the whole way if you found it interesting enough to continue this far. And if you enjoyed the video, of course, subscribe. If you have questions, you can leave a comment or email me at whatwedomath@gmail.com, or it's also in the email address in my About page. And until next time, thank you for watching.